Cool. So I'll start with this. So hey guys, this is going to be a very out of the box presentation because I did not really prepare for it. So it's yeah. So just forgive me if I say something wrong, or if you don't understand it, I'll try my best to delve into it and you can try to figure it out together. So the paper that I'm presenting today is called Pointersect. It's based on a new it's based completely on 3D reconstruction from 2D images and like the neural rendering with your cloud ray intersection. So something which is very novel in this case is basically your cloud rendering part, because that's something that's not commonly used. So as you can see from the video that we have here, so generally so what they claim is like, now not just they but everybody claims that you have point cloud information everywhere in the environment, and using that a lot of people are trying to combine this information with the real world information, and they're trying to recreate the whole environment as it is, as you have it in the real life. And this is especially important if you are trying to model something for, let's say, for XR applications. When I say XR, I mean like you have virtual reality, you have mixed reality, you have like extended reality. So that's what they want. So in order for you to have a very novel view synthesis, you need to know, or you need to also have the information about the lighting. You need to have the information where your camera is posing, where you are actually looking, and what exact object that you're looking at. So we will look into it, like how they actually try to model that. So the motivation of this paper, as per their information, as per their implementation, is first, like as I mentioned, point clouds are everywhere. You can try to synthesize point clouds from whatever direction that you have, from whatever sensors that you can get. When I say sensors, so I'll try to clear each and every point, like what I'm saying. So when I say sensors, so there are like different type of sensors that basically take this information. So for example, you have LiDAR, you have IMU, you have you have like single point cameras as well. So you basically combine all this information into one part, which is that is the phenomenon called sensor fusion, and that's what you use in order to synthesize all these point clouds. So, but one of the most important limitation of these point clouds is like you cannot actually render these points as a part of a real world environment. And that's where they wanted to, I mean, you can do a lot of synthesis, that's what people do, but you need to have a certain amount of computational power in order to do that. So they say that each point, like there's point clouds, for those who do not know, they are basically samples of surfaces, and they can be captured, as I mentioned, they can be captured using LiDAR or like continuous wave time of flight sensors and all those setups. So these representations, they provide like a straightforward connection to the location of the surface in the space, and that's why it's actually a very intuitive primitive to represent the geometry of your surface. So they they have actually given this this point. So generally what happens in any type of computer vision problem is like you have multiple, you have like one surface, and from that particular surface you will have like multiple rays that will go in order for you to recreate the exact surface that you have. But what they are trying to say is you can just try to create like the whole surface using just one point, and that's the reason like they gave this name of the paper as well, like Pointersect. And it's actually as mentioned in the paper, so it's an alternative that can directly have the ray trace point cloud by allowing one to use point cloud as surface primitive. So one way of looking into this is like you have a lot of other types of 3D representations as well. You have meshes, you have boxes, you have point clouds. So they are trying to they're trying to not go through that approach, but they're trying to like have like a whole new approach as it is. So and that's what like we'll be looking into it as well. So the method, like how they try to do is like they directly want to perform ray casting using your point clouds, and for that they introduce like generic surface ray intersection. So as I showed in the previous slide. So on the right hand side that you have, that's the ray that's the point ray intersection that can occur for formulating the surface as it is. Yeah. Okay. And in order for you to do that, they actually split the problem into two parts. So the first part is basically the surface ray intersection. So there were actually a lot of formulas in the papers which I did not really copy from there, but maybe we can check that out, and I can go directly to the paper and we can discuss that. So yeah, so the first part where they say the surface ray intersection, it's like kind of a building block operator in the physics-based rendering. So at a high level, it identifies the contacting point between a query ray, that whatever ray that goes from one object to other to the screen, and the scene geometry, so that the key information like material properties, surface normal, and incoming light at point can be retrieved and computed. So that's the part of your surface ray intersection. And yeah, so most graphical primitives, like they allow your intersection points to be easily found. For example, you have like triangular meshes. When I say triangular meshes, you basically try to do part like so for those who do not know the triangular approach of this, imagine you have like two parallel planes, and you throw your rays in that direction. So you will see like there will be a point of intersection of those rays where your rays will intersect, and that will be the point where your 3D point will actually make your 3D point into a. So you'll basically be reconstructing your 2D point to 3D point. So it's called like epipolar geometry. Yeah. So like most graphical primitives, they allow the intersection points to be easily found. For example, with triangular meshes, we can simply intersect the query ray with individual triangles, and while using the accelerated structures to reduce the number of triangular to intersect. So for example, yeah, okay, like I already gave the example. So one of the problems with this with the point clouds is like finding the intersection point between the between the rays, and that's actually that's actually one of the most one of the biggest problem with point clouds, and that is something that they claim that they did not see when they were querying a ray. So that's one of the problem formulation that they did. So surface ray intersection. Second is your cloud ray intersection. So imagine like you have like a couple of points that are sampled from the surface S. So you have like something like this. Oh no, yeah, okay. So yeah, so you have something like this. So you have a couple of points which are given. So the below one is the plane, which is P, and the above one is the surface that you have. So that is where you're trying to have like all the cloud ray intersection from there, and yeah. So from there you have like 3 points. So you have like all the points that are sampled on the surface, and you have the material associated to it as well. So as material information will have your RGB color and Cook tolerance coefficients, which I do not know what it is, like not fully like what it is. And you have the query ray that will go from the query ray is basically your camera pose that will go from one point to another to the surface. So you have these two problem formulation, and then you try to estimate the goal of it. So yeah, so in after getting these, like after getting all the previous information, you basically want to estimate these quantities. These are the unknown quantities that you have. So first is the probability that R intersects with any underlying surface of your polar plane. The intersecting point P, which is basically between your ray and your surface, and the surface normal that is normal to your plane of P. So the fourth one is actually a very it's an optional thing. These are the weights that are already present in your material property, and most of the times when you're dealing with any 3D application, you might not already have these weights. So you might have to do some pre-processing using techniques like, so there are like a lot of feature matching and feature descriptive algorithms like SIFT, SURF, ORB. So they basically give you all the points which are present in an image, and so those are the weights that are being referred here. So SIFT, SURF, these are basically algorithms like that are being used in classic computer vision, where you can find and match the points between two images and try to find like which of the points are actually which of those points are actually matching, which of the features are actually matching. And for that you also use an algorithm which is called Ransack algorithm. So Ransack basically it gives you like a whole it tries to map all the points, like all the weights in a particular map in order for you to find that particular surface. So yeah, these are the goals and these are the unknowns that you want to find. So what Pointersect is exactly? So Pointersect is a very simple neural network that they're trying to formulate. So it's a function of your ray R and your points which you want to find from the surface. Given that you want to estimate the previous four points that you had. So they were the probability, the intersection point, the surface normal, and the blending weights. So blending weights are basically optional, but still they might be of some use. So what they did was like they didn't just want to make this for few particular, like just for a particular training data. They wanted to make it more generalized. So they did two things into this. So the first thing was they utilized the fact that the intersection point is like along the query ray and the design of function that we have, so that you can estimate the distance, like in this case the distance is t from the ray origin. So the reason why they did that was actually they haven't really given the reason why they wanted to do that, but they just wanted to specify like they wanted to make this framework very simple, and that's the reason. So I can actually relate this to just classic computer vision. So in order for you to find like which position your object is, you need two parts. You need like translation and you need rotation information. So I guess that's the reason they're having this distance formulation as well, to find the origin of the ray. And the second is like they utilize this SE3 equivalence. To be honest, I do not really know what SE3 equivalence is, but it's like an optimal solution for like where like it's an optimal solution for your rotation and invariance of the 2 points. So that's one information which I don't really know in like that much of depth. So you have the information of rotation, you have the information of translating the ray and the points together. So they basically now so since you have made this more generalized, you have 6 points. You have X, Y, Z, the points where like the coordinates of the object, and you have alpha. You have the rotational information. You have the translation information, and you have the angle of that object. So using these six coordinate or 6 information, you can try and reconstruct the whole like the whole object that is in front of you using this method and the simple neural network that you have. So this is So this is the proposed model architecture that they use. So as I mentioned before, that so you have like the pre-rotation and the translation method. So what Pointersect method model actually does, it's composed of two things. It's composed of pre-processing and like pre-processing step and your transformer architecture. So what pre-processing step it does is like it rotates and translates the world coordinates such that the ray lies on the z ray axis. So as you can see from this image as well, it's all the points that are present in your point cloud. It's rotating it and it's translating it into one particular direction, and in this case, it's like the z direction. So why they want to do it is like it's kind of common sense, because you want your ray to be exact. Like you want all your points to be in that particular boundary itself, and that's the so they're not trying to find just those points which are lying in that point in that boundary, but they're trying to shift and shift all those points into that direction. Yeah, so that's one thing. So this new coordinate origin is selected such that the closest point to the ray origin lies on the z plane. So that's one reason. And so second is the transformer architecture. So your transformer architecture takes inputs, the points in the new coordinate, which you have in the z axis, and output of the learned token is used to estimate the traveling distance between the ray origin and the intersection point, which is like where does it actually intersect in the whole part. So when I say the intersection point, if I go back to the previous slide, so you can see like the bottleneck which is there, where it's all the points are intersecting. That's something that they're trying to learn from this transformer architecture as well. So yeah. Yeah, so the surface normal in this new coordinate and the h, or like the output of the sigmoid function on the logic that you have, they're used to predict the probability that the ray hits the surface, right? So it is also used as a query in the softmax function that you have. So softmax attention that you have in order for you to calculate the weights. So that's on the top layer that you have the softmax attention. So you calculate the weights from that, and finally we transform that n raised to the power r. That's the normal plane information back to the world coordinate, and make sure that it points to the opposite direction of the ray. So yeah, that's one thing. So they actually use a very small network for this. They use like 4 transformer layers and they have a feature dimension of 64 points. Yeah. So this is a very this is a very small and powerful architecture that they try to use. But the most important thing which I felt that they used to do is inverse rendering, which we will cover in some time. So yeah, so they did it in 2 points. So the rendering point clouds with intersection are doing like 2 things. They're doing image based rendering, and they're doing point cloud based rendering. So the image based rendering, basically you are given the points all like point cloud P with where each point has both the position and the RGB color, and your target camera has all your intrinsic and extrinsic matrices. So for those who do not know what extrinsic and intrinsic parameters are, extrinsic matrices or parameters, they represent the location of the camera in the 3D scene, and the intrinsic parameters represents the optimal center or the focal length of the camera. So they are like they're actually very important for you to know where your object is placed and where your camera should be placed in order to find the correct object. So you're given the point cloud, you're given the target camera information, and finally you want to compute the final color of the camera ray using the weights of these parameters into the point cloud information that you already have. So that's the CR variable that you have here. So that's one thing that they do. So this is the main idea of your image-based rendering. So you have the input point cloud, you have the like input point cloud basically have your 6 coordinates. You have XYZ coordinate, you have the RGB coordinate, and you have the query ray. So query ray basically like where your ray will be there. You apply this method and you get 4 information out of this. So probability of intersection, that's the P, that's the blue part that you have. The intersecting point, you have the surface normal, and you also get the material of the interpolation weights. So the interpolation weights are actually very interesting to say, because you don't really know exactly where your surface is or what your object is going to be, but they try to interpolate it in such a way that you have the maximum probability of where your object is going to be. So they try, so for video they try to do something called temporal consistency. So it's I'll discuss on that later as well. So yeah, so now you have, so first was the image based rendering, the second is like learning to trace the cloud. So imagine like you have a data set from like which is a mesh, and they try to do the same thing, like they try to apply Pointersect model into this, and they try to using the ray information, you get exactly what you have in the mesh data set, and they try to reconstruct the same mesh using this method. So one thing, as I mentioned, like one thing which really interested me was this inverse rendering, and that's the first time like where I'm seeing this approach in 3D reconstruction, to be honest. So basically, what this does is, like as a neural network, it allows your gradient calculation of colors and surfaces, right? But yeah, so reverse rendering is basically, actually forgot what reverse rendering was, but maybe if somebody knows here, then they can try to explain that better. So yeah. Okay. So yeah, that's the. Okay, so I have the results, but let's go and check this, the paper itself. Yeah. So from the paper, they have this result information where they, so here we go. So as you can see from, okay, yeah, this is better. So they give like few like room scaling results for this Pointersect. So you can see like the like normally if you try to do it, you can see like there are few gaps when you're trying to do the indoor reconstruction, right? And that's what you get if you're trying to do it using like normal point cloud or meshes information. Then you have this Poisson surface reconstruction, but you can see like few of the images or few of the objects that they have, it's not properly reconstructed, and that's one of the issues, right? So they have like MLBBQ model as well, which is again not that good. But you can see like the proposed one that they have, it's very clear, and that's because of the way like how they're using this ray reconstruction. And one more thing that they claim is the lighting, which is okay. This is the LiDAR information, but where is that? Yeah. So as you can see from this part, so this they claim that you can actually try. So using this proposed method, even the lighting information is very clear, but in the case of different models, they do not really see this lighting information being reconstructed very properly, and because of which you don't really get a sense of being in a real world when you're immersed in an XR application. So that's the reason like they wanted to have your lighting information, lighting very prominently seen when you are in that environment. So yeah, I guess that's all which I wanted to say for this paper. Since I did not really read it very thoroughly, so I don't think I can comment a lot in this. So yeah, one thing which they said for this paper also, and what they want to discuss as well, is like they already know, like they're like rendering speed. So in this case, I mean, if you want to do it from scratch, it actually takes a lot of computation in order for you to compute the ray and reconstruct the whole object. So there are problems with the unknown artifacts. If you already have the known artifacts in the data sets, then it can be quickly rendered and done properly. But if you have those objects which are never been seen ever by the model or by the data set, it's very difficult, and they're very distorted in that sense. They also try to do it for your normal mobile application, but right now this model or this paper, actually this paper doesn't talk about it, but in their talks they have already mentioned it, that they are not able to convert this model into a smaller or a more efficient mobile app, because it's very time consuming and again computation problem. So yeah, this is one very good paper, because it actually talks about the ray tracking, and also it's better than using point clouds in 3D capture and reconstruction. So it already proves that you can use this method instead of meshes or point clouds or voxels. Voxels anyway takes a lot of space, so I mean better to use, like we can actually try to use this for our application as well. So yeah, that's all.
Yeah, you talk about using it for our application, right? So there are a lot of key differences, right? And one of the biggest ones is the tool that you're using to measure the signal, right? So you're not using a camera with the same kind of, it doesn't have that same geometry, right? As you're dealing with K-space and the MRI, and even if you have a point cloud model of the brain, the tool that was used, or I guess, well, how do you see this translating? Because I'm not really sure with these spaces being so different, the geometry being so different.
Right, no, that's actually a good question. So the reason why I mentioned that is because you already have the information on your point clouds. So but yeah, actually I get your point. So in this case, they're doing everything from scratch. They're taking all the the camera-based position, and they're trying to render it.
Right.
But they're not trying to convert it from one 3D point to another, like 3D format to another 3D format. So I guess it does make sense if for you. I don't think you can do that, because
I'm thinking. I mean, so the stuff that Williams and Lindland are doing with the mesh reconstruction is like the most obvious first analog. But I don't see that like how this would be used.
I think we also already have the meshes. We don't have
exactly
just the point cloud. We start with we actually have the surface already, and then we sample the point clouds coming on. So it's like different, the other way around almost.
With just point clouds, they can also draw it.
No. You can get the point clouds. I'm just saying, like, we also have the mesh, right? Like,
no, if even if we don't have the mesh, we only have the points. You only have an array of like 3D.
No, I know. I'm just saying, like, out of FreeSurfer, it's not like it gives us the point cloud and we still have to compute the mesh. It gives us the mesh, right? It fits into a group mesh.
But it starts with the voxel space, which I guess could be thought of as.
Yeah, but it's just a Euclidean.
I don't know. I'm not seeing the translation immediately.
So I guess
it's got to be some weird thing you could do.
Yeah, you can.
There's always something.
So they talk about this, like section 4.6. You have like real lidar scan point clouds. So you already scan the point clouds, and like even though it's like trained on different data sets, they are trying to downsize it and then try to convert it to this ray. And then they're trying to reconstruct it using this method. So that's where I thought like this can happen. But yeah, I guess for fMRI, there will be like added challenges to do it.
I mean, so the definite thing you could do is, people who are doing like behavioral tasks that involve recording video of the subject, you
Mhm.
have 3D information about the subject, maybe multiple cameras in the scanner or something like that. But so that would just be a direct, you would be using visual information that it doesn't touch on processing the MRI, you're just
Yeah.
using computer vision stuff.
So they did try something like that. So it's, I mentioned this word, right, temporal consistency. So what temporal consistency is, like you have a whole video, and from that video you try to either reconstruct your whole scene, or you can either reconstruct it using point clouds or meshes. But the point about it is, imagine it like you have different type of images and you want to stitch all these images. When you get the output, you will see like there are inconsistency between those images, right? So that's where that's where your temporal consistency come into picture. So it will try to predict like which scene was actually similar to the next scene, and then it will try to stitch the exact same features. So they did say that in their talk, but I did not see this information in their paper for some reason. So yeah, maybe for videos, yeah, you can try to do that. But yeah, it's so one thing like what that I mentioned, right? Like inverse rendering. So I'm seeing a lot of people who are trying to put this into their applications. Although I swear I knew the definition of inverse rendering, but right now I forgot it. So yeah, it's something that's actually very interesting, because what you're doing is you're constructing a whole object, and then you're deintegrating the whole object again in order to find those points which are very important. So that's like, it's something which I found really really interesting. So yeah, that's one thing. So yeah, I guess that's all. If you guys have any questions, I will try my best to answer it.
Just curious to see what applications you find.
Yeah, thanks
Also,
for now.
they're doing it for mainly for AR VR applications. Because they want you to have like a very immersive experience when you're inside any AR or VR environment. So one of the things which they mentioned is, like for example, in Meta, like whatever Meta is proposing right now as well, right? Even if you go inside that environment of AR VR, you won't really see a very realistic environment. Like you won't see the objects which are real world like. Also, you won't see the shadows like how we see it in real life. So that's one thing that they wanted to focus on.
Could potentially be useful for cognitive tasks, right? If you wanted to simulate something like that,
Yeah.
have somebody do a behavioral task, but it really wasn't like, something that would be easily implementable
Yeah.
Right.
in the MRI, space.
That's
Yeah,
what
there's folks that they're going to give a talk at DMAP in June, but they from the sport therapy center that came a while ago and did stuff related to injury recovery and virtual reality that may be interested.
Yeah, they do a lot of stuff like that at Emory.
Yeah.
Well, also think about quick rendering of the brain, like MRI CrowdGL has, and maybe we can have Mohammed had it in browser and BrainShop, but because we have voxels points, can we like render 3D looking just for visualization and rotation? Will it work? I wonder.
I'm not really sure about that.
Okay, thank you, Mrinal, and yeah, that was pretty good for until unprepared talk. Maybe we should randomly assign people and see what happens, like 1 hour before. I'm sure it won't work for Sajjad though, but yeah.
No, I'm pretty sure I would have given more information and like how exactly you can go in all the equations that they presented, but yeah, that this is the best I can do in like 20 minutes, 15 minutes preparation.
Pretty good.
Plus people don't want to hear
Thanks.
that most of the time, so.
Yeah, don't forget about today's DMAP talk is in BSI, and it's about, I don't know, how to manipulate people or something. I just, it sounded to me how to manipulate people, but how to change their state of mind. So I'll see you later, and yeah, thanks everyone. Bye bye.